Hi folks, and welcome back to the live stream for Calculus 1. Today we're going to be talking about continuity, go over briefly epsilon delta proofs, and then touch on derivatives, the definition of derivative in particular. If at any point in time you have questions, please, there's a chat box over on the right hand side. That's what I'm here for, so ask your questions and I'm happy to answer. If you're paying attention too, there might be some bonuses along the way too. So I want to briefly cover, well, this won't be so brief. There are some struggles in continuity. I want to make sure we address them and kind of show the importance of continuity. So what is continuity? Basically, you say a function is continuous at some real number c. I know this looks kind of crazy, but when you have the limit as x approaches c of f of x equaling f of c, meaning you can plug it in the function. So the way we always kind of think of it is when you're drawing the picture, what you'll hear oftentimes is if I'm drawing with a pencil, I never can pick my pencil up when drawing it. And so that would be an example of a continuous function if I drew something like that. So now, say we have a function f of x being continuous on its domain if it's just continuous at every real number c in its domain. So with that in mind, we're trying to show that functions are continuous. So we'll look at a few things. So we're talking about continuous on domains. So first things first, let's talk about what does it mean to be the domain. So find the domain of the following functions. So we have a few, just brief overview. Now, with f of x, let's take a look. You have the 3x to the 7th. This is continuous for all real numbers. And that's a shorthand, that fancy looking R there. That's a shorthand for all real numbers. And why is it continuous for all real numbers? Because you can plug in any real number. There's no values that you can plug into x that will make it not exist. However, on this second piece, this 9x plus 11, you need that 9x plus 11 is greater than or equal to 0. And so to simplify that, we get 9x is greater than or equal to negative 11, or x is greater than or equal to negative 11 over 9. Now, a way we can do this, where some people struggle, if I put negative 11 over 9 right here, and then it's greater than or equal to, so we put a solid dot. Which direction should we go in? Well, since it's greater than or equal to, we must go to the right. Now, oftentimes we want to write this in interval notation, and so the way we do that, since we're including negative 11 ninths, we'll put negative 11 ninths, and then we go all the way to infinity, and then put a parentheses, because we can never touch infinity. So that's one example. People get nervous with square roots. All you're doing is just setting up an inequality, no big deal there. For the second one, a lot of people panic on these piecewise functions. So what we do is there's a couple things. We have restrictions. So for the first case, we're looking if x is less than 0. Second case, only if x is equal to 0. And the third case is if x is greater than 0. So what we'll do is we'll look at each function in particular. So we'll start with the 5 over x plus 2. When is that thing not defined? Well, x plus 2 cannot equal 0, meaning x cannot equal negative 2. Notice negative 2 happens to be within this range. So that means in this first case, x cannot equal negative 2. Okay, so we have no problem. We have a problem with that one at x equals negative 2. So in the second case, 17, notice that's always going to be continuous. We have nothing to worry about there. So this one's just kind of checked off. In the third case, we need to look when is the denominator equal to 0 there. Well, it's when x plus 5 equals 0, so we'll put x plus 5 cannot equal 0. X cannot equal negative 5. But notice, negative 5 is not within this restriction here. So since it isn't, negative 5 is less than 0 rather than greater than 0, this one's also checked off in terms of being continuous on that interval. So at the end of the day, the only problem point that we had in this piecewise function is x cannot equal negative 2. And if you like drawing, you can do that again. We'll put negative 2, but now we need an open circle and you go in either direction. All right, so what does that mean if you draw that out? Well, it means you can go from negative infinity all the way to negative 2. But we don't want to include negative 2, so that's why we put an open parentheses, union, negative 2, and then we can go all the way to positive infinity. And we're done. Okay, hopefully so far so good. If not, just let me know. Moving on to h of x, what's the tricky thing about this? Well, you have two different functions, and they both have restrictions. So in this case, you have 8 minus x is greater than or equal to 0, and you have on this one, x plus 8 is greater than or equal to 0. So notice, if we move this, you get 8 is greater than or equal to x, and x is greater than or equal to negative 8 in the second one. So what happens? Well, I'm actually going to draw two intervals. So we'll draw one interval there, and we'll draw another interval here. And just to make sure, I'm going to put 8 on one of these, and then we'll put negative 8, so they're in their respective orders in terms of what's happening. So in our first case, we'll do 8 greater than or equal to x. What does that look like? Well, you'll have a solid dot here, and 8 is larger than x, so that means we got to go back this way. Okay, and in the second case, so we have x greater than or equal to negative 8. You start at negative 8, and we want the x's to be bigger than that, so we'll draw it this way. Now here's the deal when you're looking at domain. When we have two pieces like this, to combine it, to take a look at h of x, what do we need to do? Well, we're looking at the overlap of these two. So notice in the first case, anything beyond 8, we have a problem. So what we'll do is we'll just draw this dotted line all the way down, and here's 8, and there's our solid dot. We are not going to shade in the stuff to the right of the solid dot. In a similar manner, anything to the left of negative 8. So the first part it would have been alright, but the second part it wouldn't. So we put negative 8 down with a solid dot, and we want to fill that in. And so we're filling in all that middle piece. So what is the domain of our function here? Well, notice we want to include negative 8. So we go negative 8, comma, and then we finish it off at positive 8. And that's it. Okay, so now we see domain. Now we can start to talk about continuity at a point a little bit more and hopefully get into continuous functions. Determine if the following functions are continuous at x equals 4. Well, first off, there's two things you need to check. So the real question here is, does the limit as x approaches 4 of f of x equal f of 4? So in this case, the first one, actually I'll even draw a graph here. So first off, if we have a graph, we have these vertical asymptote there. This is the graph, let's say g of x equals 1 over x squared. And notice what we've done to this graph. You see an x minus 4 down below. That's essentially shifted the graph 4 units to the right. So we go 1, 2, 3, 4, and we're going to draw the same graph. Now, by the looks of the graph, hopefully you can tell, and this is, by the way, f of x equals 1 over x minus 4, the quantity squared. You can tell where the limit's going. Both are approaching that vertical asymptote, going towards infinity. So, in fact, though, if you, let's say you didn't know that, you want to do limit as x approaches 4 of 1 over x minus 4, the quantity squared. Notice, since we're squaring down below, we're always getting some positive number, or 0. In fact, when we plug in 4, notice we would get 1 over 0. So that tells us we're either going to have either does not exist, or infinity, or negative infinity, essentially. So, but since it's always positive from both sides, we're getting like 1 over 0.0001. Well, that blows up to like thousands, and then millions, billions, depending upon how close we're getting to 4. So what that tells us is this limit actually equals infinity. That right there, that alone actually tells us this can't be continuous. And the reason why, so not continuous, Because the way we define these functions, we don't say f of 4 can equal infinity. There's no equal to infinity in these cases. So that tells us right away that's not continuous. In fact, we'll talk about later, this is an infinite discontinuity, essentially what's happening there. All right, in the second case, a little bit more work. We got to check out a left and a right hand limit. And technically, I could have done that left and right hand limit in that first case, but I was trying to somewhat shortcut it. So in this case, limit as x approaches 4 from the left of g of x. Which function do we use? Well, notice if we're approaching from the left, that means less than 4. So that means we're looking at this scenario, so we got to look at that function. So this is limit as x approaches 4 from the left of 4x. And so that should equal 4 times 4, which equals 16. If we take the limit as x approaches 4 from the right of g of x, well, that would be numbers greater than 4. So we're looking at this third scenario. So we get the limit as x approaches 4 from the right of 32 minus 4x. And so let me know. I'll give you a chance to work it out. What does that limit equal? And you can type it in the chat box there. Very good. Jeremy, go ahead and send me an email later. Since you got it, you got 16, that's right on the money. You get an eagle egg, so you'll get a bonus point on this upcoming homework as well. So now that we have that, we have noticed the left and right hand limit are equal. That means, since they're equal, the limit as x approaches 4 of g of x equals 16. Okay, and you're welcome. So now, moving forward from here, what do we need to check? Well, we need to compare that to g of 4. So what is g of 4? Well, that's this scenario, right? And so notice we get 0. Okay, so notice we have limit as x approaches 4 of g of x does not equal g of 4. So that means it's not continuous at x equals 4. In fact, we have a special name for this type of discontinuity. So what's happening on the graph, by the way? If you have the graph here, let's say 4's right over here. So you have the solid dot appears right here, and for x less than 4, you're at 4x. So it's way up here, but hopefully we get the gist. It's an open circle, and you get a straight line here, and then you go 32 minus 4x, and you're basically coming back down this way. So that's what's happening with the graph. You get this removable discontinuity. That's what we call a hole, essentially, in the graph. And so that hopefully gives you a better idea as to what happened on this piecewise function because you had a match up. All right. So moving forward, this one gave some people some tripping up. It scares us at first, but when you realize what you have to do, it's hopefully not too bad. So in order for this to be continuous at x equals 2, first off we need, so there's a question, if your limit does not exist, is not continuous. Yeah, that's exactly right. So if you have a limit that doesn't exist, you're done, not continuous. So yeah, as a matter of fact, if you had like, if I go back here, let's say I looked at the function, I already used g of x. Say we looked at the function h of x equals 1 over x minus 4. You aren't going to have a limit as x approaches 4 because your left-hand limit and right-hand limit aren't equal. Your left-hand limit's negative infinity, your right-hand limit's going to be positive infinity. Just an FYI, the graph looks something like this. So you get a curve there. Don't let your eyes fool you, those are perfect curves. But basically you've shifted the graph of 1 over x over 4 units. So that one doesn't exist, so you're done. That's all you need to show. Now, there might be questions like, what's your left-hand limit, what's your right-hand limit, and all that jazz, but really, that's all you're doing is just checking limits left and right. So, in this case, yeah, you actually have to check to see It's 2 is the magical number. And notice, anything other than 2, we have a polynomial here. You do have an x minus b down below, so we'll have to watch out for what the b value is, but hopefully that'll make some sense in a second here in terms of what we're trying to do. So you have is continuous at x equals 2. So first off, we need the limit as x approaches 2 of f of x to equal f of 2. Alright, so you can always calculate f of 2 real quick. Notice we get negative 24 over, it'd be 2 minus b. That equals f of 2. But I'm not really going to focus on that just yet. What I want to focus on is order for this limit to exist. Well, in order for the limit to exist, you need the limit as x approaches 2 from the left of f of x to equal the limit as x approaches 2 from the right of f of x. And notice the 2 from the right is going to match that function that we just evaluated at f of 2. So in the case of limit as x approaches 2 from the left, notice that becomes, well, this scenario up here, we have the b minus 2x. So we just plug in 2 in for the x. So you get b minus 2 times 2. A lot of people get confused because there's a b in there. Remember, it's the x values that we're plugging in for. So in a similar manner, oh, sorry, I got ahead of myself there. So that's the next step on down. This is b minus 2x. And in a similar manner, the limit as x approaches 2 from the right, you have negative 24 over x minus b. And now you can plug in 2 for both of those, and you get b minus 2 times 2 equals negative 24 over 2 minus b. This makes b minus 4 equals negative 24 over 2 minus b. And moving forward from there, how do we solve this? Multiply both sides by the denominator, and then notice it'll cancel off the denominator on the right hand side. So you have 2 minus b times b minus 4 equals negative 24. Multiply that on out, you get negative b squared. So you'll have a positive 4b with those two. You'll have a positive 2b with those two, so that makes a positive 6b. And then you'll have a minus 8 equals negative 24. Let me start it up here. Okay, moving it over to the other side, you get 0 equals you have b squared minus 6b. When you add 8 to the other side, I believe that gives you minus 16. So notice you get 0 equals b minus 8 and then b plus 2. So from there you get b equals 8 or negative 2. And so we have our solutions and we're done there. And by the way, you might say, okay, wait, you forgot about the equal to part. Well, technically I didn't, because if you notice that appeared right here. Okay, so hopefully that makes sense. If there's any questions, just let me know. But you do that over and over and over again for a lot of them. But so notice that's continuous at x equals 2. And so what we want to expand to is continuous on certain domains, right? And so find all values of the constant k that makes f of x equal kx squared, and then negative 9x plus k. Oh, actually I should go back. I should do one last double check here. There is one thing that I need to make sure. For x equals 2, notice the only thing I couldn't have happen, I can't have this be 2. It wasn't a deal breaker here, because notice our values were negative 2 and 8. If 2 would have popped up though, that's something I needed to watch out for. So just watch out there, because then it wouldn't be in our domain. That goes back to the domain business. So, but instead we got x, and it becomes plus 2 down below, so we're all good. So yeah, just a brief mention there. We don't have any fractions in this one, and so since these are polynomials, they're continuous everywhere, with the exception of the breakpoint right here. Okay, so with that being the only point where things could possibly be broken up, all we have to do is check the limit as x approaches 6 of f of x and make sure that that equals f of 6. So it's the same song and dance pretty much. The only thing is we had to detect where we needed to look. So in this case is 6 is our values. Now if you have 3 inequalities, you've got to check a few more, but same thing, you just check the left hand limits and the right hand limits. And so as we go left hand limit of f of x, that has to equal the right hand limit of f of x. And you don't need to necessarily write out all these extra steps, but I just want to make sure we're aware as to what's going on. The left hand limit, that would be this top function. So you have kx squared essentially, and the right hand limit would be the second function. Okay, so you want a few other extra steps. So the question was, yes, please, steps are good. Showing those extra steps. I'll try and keep them included. So, and if I move astray, please let me know. Just let me know where you need to be caught up on. So, okay, so moving forward, plugging in now. So we have that both of these are continuous, and so we can plug in the limits. So you get k times 6 squared equals -9 times 6 plus k. So notice this is 36k equals -54 plus k. So this one might not be so obvious. So when you subtract the k from both sides, you get 35k equals -54. And so that gives us k equals -54 over 35. And then there's one other thing. What is f of 6? Well, if you notice, f of 6 has to happens to deal with the first scenario. So f of 6 would equal k times 6 squared, which we've already accounted for, so there's nothing to worry about here. In terms of, we've already used that part, and that was used on our left-hand limit, so we've already accounted for that. We're good, and so that means this k value, and since there's no restrictions, this would cause it to be continuous everywhere. And that's why I really like the algebra and calculus here, because that might not be a number you're going to think off the top of your head. But if you use left-hand limits, right-hand limits, and function values and all that stuff, you actually get your answer. So hopefully that makes sense on that. So we'll move forward to the next one. What are the types of discontinuities that we run into? We actually already ran into a couple of them. What do they look like, and what are we talking about? So infinite discontinuities. So you can have things of this form. Limit as x approaches c from the left of f of x equals positive infinity, or limit as x approaches c from the left. Well, actually, it could be positive or negative. Limit as x approaches c from the right of f of x equals plus or minus infinity. Things of that nature. Obviously, if the left and right hand limits are equal, then you get positive infinity or negative infinity. They could both go in the same direction. So just to give you an idea of an infinite discontinuity graphically, you could have some function that does all sorts of funky stuff, but then makes a turn there, and then maybe it goes on the other side. They could be on the same side. So I could have this going from positive infinity on down. But that's an example of an infinite discontinuity. Okay? Removable discontinuity. Oh, and by the way, the function value itself, so f of c doesn't really matter. It's the limits that matter on the infinite discontinuity. So I could have a function value where it actually approaches something at that discontinuity. Not really making a big deal, though. In terms of the removable, though, this is a little bit different. You have the limit as x approaches c of f of x, and oh, by the way, so let's say this value is c. That has to equal some other constant where L is a real number. Okay, so what happens here? Well, basically you have this hole in this graph. And that's C, and then let's say this would be L. Okay? Because it's the corresponding Y value. That's all that happens. You can't have those two things being separated on the left and right hand side. They have to approach the same number on both sides. Now, you can also toss in, if you want, can be things like this too, right? And that tends to trip people up, but that's allowable, right? But the removable discontinuity means we have a hole somewhere in the graph. Okay, and we already encountered a case where we had this point somewhere else and then the hole in the graph. So, but in terms of the jump discontinuity, you have the limit as x approaches c from the left of f of x equals some constant L, and the limit as x approaches c from the right of f of x equals some constant m. You have, in this case, L and M are real numbers. With L not equal to M. So let's say you have all this funky business, and then maybe, let's say C is here this time. So you can have, I'll put open circles to start and then kind of fill in from there. So say this is your function. In this case, I'm putting M up here because it's approaching from the right, and in this case, L is down there because it's approaching from the left-hand side. So now you can fill in these dots on one side. You can't fill in them both, though, because then it wouldn't be a function anymore. But so I could have something like that, and that's essentially what happened. And if you do the piecewise function and you chose any other values of k in that last problem. So hopefully that allows us to see the different types of discontinuities, and let's see them in action and see if we can detect which one's which. Okay, but it all involves limits is the main thing. You're just looking at limits, and that does the trick. So say we have this function f of x. The first thing what we'll do is we'll find the domain. Okay, so it's kind of piecing this stuff together. The domain, well, notice we need to break this down. F of x equals 7 times x minus 1 all over x squared. And then notice, I'll do this the long way, then we'll kind of break it up real quick. X squared minus 7x, and then plus 6. I don't want plus 6. Yeah. Okay. So now, moving forward from here, that becomes 7 times x minus 1. Notice we have an x squared. And how can we break this up? Well, you have an x and an x. It's a minus in the middle, and plus is multiplication, so that means we have two minuses. And the only factors that add to negative 7 and multiply to positive 6 are negative 6 and 1. So that tells us we set each factor equal to 0. For our domain, we have x squared, or, well, I say equal to 0, but it can equal 0, essentially. X squared cannot equal 0. X minus 6 cannot equal 0. And x minus 1 cannot equal 0. So this means x cannot equal 0, 6, nor 1. So if you're looking at our domain, if you want to write it in interval notation, you go from negative infinity to 0, union 0 to 1, union 1 to 6, union 6 to infinity, and beyond. Okay, so that's our domain written out, but that's not the big ordeal. We want to find all discontinuities. So the discontinuities are going to be 0, 6, and 1. And all we need to do is find limits involved with this. Okay, so limit as x approaches, let's do 0 and see if we can actually evaluate that of f of x. So notice when we plug that in, you get the limit as x approaches 0 of 7x minus 1 all over x squared. And the reason why I just plugged in 0 rather than 0 from the left, 0 from the right, is because of this x squared business. You can actually start it from x from the left and x from the right as well. So here's the deal. Notice when we plug in 0, you're going to get 0 down below. So that means you have 0. What do you have up above? You have a negative. And actually, you know what we could do, to be honest, when we're taking the limit of f of x, you can simplify this. You can take the x minus 1s on out of here. Okay? And what that allows us to do, because that's what we're simplifying at the end of the day, it makes this an even simpler problem. So you have 7, which is some constant, over 0. So it's going to be either infinity or negative infinity, or it does not exist. But since we're squaring it, it's always positive. So this is positive. And notice when we plug in 0 here, we're getting a negative as we approach 0. Okay? So positive times negative means a negative. So this whole thing has to approach negative infinity. What does that mean? Well, we got an infinite limit. That means an infinite discontinuity at x equals 0. In a similar manner, we have 6 next. I'll take 6, but we'll go from the left. So you get limit as x approaches 6 from the left. Same thing, we can cross off the x minus 1s because we are talking about limits. Now think about that. We got a positive on top, we got a positive down below. That means this is a negative because we're approaching from the left hand side, because it's like 5.99, which is a negative 0.01. So this would be negative infinity because we have essentially something approaching 0 really fast on the denominator, and it's approaching it from the negative side. Okay, so that tells us just the left-hand limit alone. If you want to check the right-hand limit, just change that to a plus and a plus, and then notice since you're approaching from the right-hand side, you're starting at like 6.01. That's going to be positive, and that would be positive infinity. But just that left-hand limit alone tells us that we have an infinite discontinuity at x equals 6. The next one, limit as x approaches 1 of f of x. Notice the 1's dropped out. Right? So this is the limit as x approaches 1 of now, with no more x minus 1's in there after we simplify. Okay, so you have 7 over x squared, x minus 6. And so this becomes 7 over 1 times 1 minus 6. So that's negative 7/5. However, f of 1 does not exist. So we have a limit that's a constant on both sides, and the function value doesn't exist. So it is a discontinuity, and what type is it? It's a removable discontinuity. And by the way, what does that mean? It means we got a hole in our graph at the point 1, negative 7/5. Oh. Sure. So I see a question. Could you explain how you got negative infinity from the denominator again? Yes, so I'll assume it's the 6 one. And if not, if you want to see it on the 0 one as well, just let me know. So at the end of the day, we know that this thing, yeah, okay, so the negative 6. So in this scenario, what we're going to have is 7 over, it'd be 36 times 0 if we were to plug in. So that means this is 7 over 0 essentially. So we know it's going to be infinity or negative infinity. And when we're approaching from the left-hand side, think of the numbers that we're approaching. So we're doing numbers like 5.999, right? When I plug that in and square it, notice I get a positive, right? So we're just trying to determine positive or negative infinity because we have some constant over 0, right? And so from there, though, if you think, plug in 5.999 minus 6. Notice I get negative 0.001, but I don't care about the number itself. All I care about is that negative symbol. So it's that negative symbol that does the trick, and that tells me, okay, so this is, we have a positive up top, a positive and a negative down below. So that makes negative overall. So it has to be negative infinity. Okay? And so in the other case, I'll actually go through the other one just so you can see it. Limit as x approaches 6 from the right. So we have x squared over x minus 6, right? Now notice in this case, these would be numbers like 6.0001. But if I'm plugging that into this x right here, what are we getting? We're getting a positive number. The 7 just, that stays still, that's still positive. But when I go 6.0001 minus 6, notice I get some positive. Okay. Oh, and the reason, I'm getting ahead of myself there. You have 7 over 6 squared essentially times 0 one more time. So this is a constant divided by 0. So what that means is we're going to be blowing up towards infinity. And if you don't understand that, think of this. If I go 7 divided by 0.001, that's equal to 7,000. Right? If I go 7 divided by 0.00001, that means I got to add 2 more zeros to that 7,000. Right? So as I get closer and closer to 0 here, notice this thing's just blowing up overall. Okay? So yeah, in terms of the pluses there, hopefully that makes sense in terms of now we're trying to, we have plus, plus, and plus, so all those are positive, so it has to blow up towards positive infinity. Right? Basically all I'm doing is plugging in some numbers that are somewhat close. That's all it really is to it. The 36 is kind of inconsequential. It's really not doing much overall. As you get closer and closer to 0, that 36 is going to go away real fast. So, okay, glad you have it now. And so, and that's exactly what I want. If you have any more questions, just let me know. So, did I skip a page or am I good? Okay, yeah, we're good. So continuity and limits. What's the big deal with continuity? Why do we care? What it allows us to do is it allows us to bring inside these limits. You can bring them inside functions. So if you have a continuous function on the real numbers, then what you can do, if you have limit as x approaches c of f of g of x, you can go f of limit as x approaches c of g of x. Just look at the inner function. That's going to come into play tremendously later on in the semester when we get to like L'Hopital's rule. So you got a flavor of it in one of the problems. And it's this. If you notice if we had just sine of x, that is a continuous function, right? So what that allows us to do is that this whole thing equals sine of the limit as x approaches pi of x plus sine of x. So continuity is what allowed that to happen. You can bring the limit inside. And so now we can apply it to both pieces. And so you get equals sine of, well, you can just plug in, you get pi plus sine of pi. Now I don't know how we are on trig functions and all that stuff. Everyone's got their own thing in terms of whether they understand them or not. What I'd always recommend, say you don't know this off the top of your head, there's a way to kind of memorize it. The first thing to understand is the unit circle. Okay, the unit circle is given by this crazy, sort of not so much known properties, but it pops up mostly in Calc 2. So you have this x squared plus y squared equals 1. Yeah, so sine of pi is 0. Yeah, that's exactly right. So, yeah, you have it down pretty good. And just in case, I want to try and make sure that everyone else does when the time comes. So you get sine of pi is 0, and so sine of pi equals 0. So let's say you have a worst case scenario come exam time. If you know how to do the labels on this, you go 0 pi over 2 pi, 3 pi over 2, and then 2 pi happens over at that axis again. What you need to remember is the x value corresponds to cosine of theta and the y value corresponds to sine of theta. So notice, when you're at sine of pi, rather than ask a question, you go over here. What are the coordinates? Well, if it's x squared plus y squared equals 1, you know that this is going to be 0 for the x and negative 1. Oh, not 0 for the x, sorry. Negative 1 for the x. Sorry about that. Negative 1 for the x and 0 for the y. So when you look at sine of pi, I'm just looking at that coordinate right there. So that's all there is to it in terms of, so this is sine of pi. If you're wondering about cosine of pi, and you can manipulate this for the whole thing. Now, the only other ones you have to watch out for are things like pi over 4, and pi over 4 times any multiple of pi over 2, and same thing with pi over 6 and pi over 3. Those are the main angles that you're going to need to know at the end of the day. So, no more questions on that piece. We'll move forward to the intermediate value theorem. This tends to be tricky, but I think after you see some visualizations in terms of what's happening, it's kind of intuitive. So there is some key components. The first part, if you have f of x being a continuous function, I can't emphasize that enough, continuous function on the interval, closed interval AB. So if you have that, and let's say L is a number between f of A and f of B. Okay, so first off, you see A here, and I'm going to put f of A. It doesn't mean that B has to necessarily be well, B would be further down the line from the interval, but it doesn't mean that f of B, which would occur up here, has to be above f of A. It could be below. But we want L to be a number in between there. So it doesn't matter where I choose, but if I choose any number in between here, let's say I chose right there, and that is L. Then what's happening? It says somewhere on that interval from A to B, so we're going to go inside now, this interval, there's going to be something that pops out and has L hit. So now L, just recall, if I write y equals L, and don't let your eyes fool you, that is a perfectly straight line. Y equals L is right here. The value that we're referring to, see how it intersects the graph right there? It happens to be that this would be the so-called C that we're looking for. Now, why must that happen? Well, no matter how I draw the graph, let's say I erase this, this inner piece, and let's say I wanted to avoid it now. Say I want to avoid hitting L. Is it possible for me to do? So remember, I have to keep this function continuous, and I want to try and never hit L. Well, notice, if I'm keeping this function continuous, no matter how I draw it, sooner or later, I'm going to have to go up and hit that red dot where B, f of B is. So that means, in order for me to do that, I have to cross that line. And so now, in this case, this would be the C value, right? And this happens over and over again. It's the fact that the whole no picking up of the pencil idea. So you're going to cross that line sooner or later. That's what the intermediate value theorem is getting at. So let's take a look at a problem. Consider a function f of x equals 9x minus cosine x, and determine if there exists a root of f of x on the interval 0, 1, closed interval 0, 1. So first off, let me be honest with you. I have no idea what this graph looks like overall, like exact value wise. I could give you a ballpark as to what's happening, and I know how it's going to start to approach when it approaches infinity and things like that. But in terms of what the actual behavior is, where these roots would occur, oh crud, sorry about that. I thought I was plugged in. Okay, there we go. Sorry about that little hiccup there. So now, consider the function. Can we determine if there exists a root of f of x on this interval? And how do we do it? Well, it's actually quite easy. So first off, f of x is continuous. since y equals 9x and y equals negative cosine x are continuous functions on all real numbers. Okay. Oh, sorry about that. So I see the hum came back to the headphones. Yeah, I don't know. Let me see if I can fix that. Give me 1 second. Was that able to fix the humming? Okay. Yeah, sorry about that. Yeah, it's just battery running low, plugging it back in, I think. So on this part, moving forward, so what we have is continuous. It means we're hopefully going to be able to apply the intermediate value theorem. So you have f of 0 equals, so notice, f of 0 equals 9 times 0 minus cosine of 0, which equals negative 1, and f of 1 equals, this would be 9 times 1 minus cosine of 1. Now you might say, oh, what the heck is cosine of 1? I'm not, in terms of the cosine of 1, I'm not exactly sure off the top of my head in terms of what exact decimal it is. But I know cosine ranges between negative 1 and positive 1. In fact, I can tell you cosine of 1, it's going to be, actually, so cosine of 1 is not 0. It's a little bit different because when you look at your unit circle, you have 0 and pi over 2, right? And pi is 3.14 over 2. And so that means your angle 1 is actually somewhere in here. And so what you're looking at, if you're looking at cosine, you're looking at this corresponding x value. So I don't know what the heck that is, to be honest with you. I mean, so, but at the end of the day, it's just going to be some positive number. So with it being some positive number, all I really need, though, is that this is greater than 8. Okay? Now, that won't do any harm, right? The main thing, what we're going to use now, since 0 lies between negative 1 and 9 minus cosine of 1, the intermediate value theorem, and you might abbreviate this IVT, states that there exists a C in the open interval now, 0, 1. And the reason we shift to open interval is because you notice what 0 and 1, you plug them in and you didn't get that answer. Such that, okay, so now what happens? Such that f of c equals 0. And that's exactly what we wanted. So the intermediate value theorem, it won't necessarily tell us where exactly that is. Now, we could always limit that interval smaller and smaller to try and get there, and there's this approximation idea. But at the end of the day, all we care about is the existence. So, and that's the whole idea with this intermediate value theorem, existence. In fact, rather than root, okay, so exists or root. So, yeah. So that's this last line. So what does it mean to, so the question, what does that mean for a root to exist of f of x? It means, can f of x equal 0? So that's all it is. Yeah, and so the c happens to be in this interval 0, 1, and that came from our interval that we chose here. Okay. In fact, you could choose c to be in between 0, 2, 0, 3, so on and so forth. And in fact, we can even change the roots to any number. between, let's say, what was our lower bound there? We had -1 and 9 minus cosine of 1. And the reason why, I'm going to actually refer back to that previous page. If you take a look, it was any number. Notice we chose L. I said, hey, it doesn't matter as long as it's in between this f of a and f of b. Any of those numbers can work, right? Because notice we cross every single point. So if I even took this line here, oh yeah, we hit that. And then if I take this line way up here, it might be a little bit longer, but as long as it's below there, oh yeah, what do you know? We hit that one too. All of them they end up getting hit by the intermediate value theorem allows that to happen. So it's that continuity is that key component. So that's why when we use the intermediate value theorem, you need continuity. If I don't have continuity, I can start to jump things and have them all sorts of messed up. So kind of building to the table